Waste, the topic that every engineer, scientist, and even politician is trying to solve currently. There are actually various types of waste, which include organic waste like the banana peel that you throw on the street, and most likely people will slip on like in the movies, plastic waste that polluted the oceans and hurting life underwater, metal waste from the can of Coke that someone might finish last Friday, and other types of waste. Now, in Indonesia, around 175,000 tons of these various types of waste are produced daily, and sadly, only 7% of the waste is actually being recycled, while 69% is actually left as landfill waste. Sadly, this number is expected to increase rapidly in the next few years. Actually, according to the hierarchy of waste management presented by European Union in 2008, prevention of waste production is preferred. But sadly, it is known that reducing the amount of waste produced in a large number will not be achieved in the short term. So, what is one of the available and feasible options that we can do? Hydrothermal carbonization, or is known HTC, is a wet, moderately low temperature process of decomposing organic materials into carbonaceous residue. It happens in 180 to 350 degrees Celsius and at atmospheric pressure. Essentially, it is like the process of fossil making, but only a million years faster. For this process, mixed waste streams from landfill waste that do not need to undergo sorting can be used directly as HTC reactor feedstock. This is extremely impactful to the environment because mixed waste streams are usually hard to manage since food waste decomposes very quickly and produces leachate, which can lower the quality of plastic for it to be recycled. The only pre-treatment to do is the recovery of metals, since metals can be easily removed with magnets. The process flow of HTC is fairly easy. First, metals will be separated from papers, plastic, and food waste by using magnetic separator to be recovered and resold. Next, the remaining mixed streams will go inside the reactor inside an oven at around 250 degrees Celsius for 20 hours. After that, the reactor is removed from the oven and subsequently placed in a cold water bath to quench the reaction. After cooled, hydrochar is ready to collect and used. Hydrochar yields range from 29 to 63%, depending on the composition of the feedstock. For regular mixed municipal waste, hydrochar yield rockets to 63.2%. When we compare it to lignite, the most used type of coal in Indonesia, hydrochar actually has higher HHV or higher heating value over 6 megajoule per kilogram, with HHV of lignite being 14 megajoule per kilogram and hydrochar being 20 megajoule per kilogram. Not only that, moisture content of hydrochar is also lower than lignite, hydrochar being 6.7% and lignite being 7.6%. But hydrochar consists of 37.9% ash compared to lignite of 7.9%, making it one of the biggest drawbacks of hydrochar. Moreover, many side products are generated during this process, which include furan, ethanol, and hydrogen. Fortunately, these residues can be further utilized into a more practical products such as high ash content for zeolites, commercialization of furan, and alternative use of ethanol and hydrogen for energy generation. Now, if seen from the business perspective, HTC's total production cost is merely low, standing at around 157 euros per ton of hydrochar produced, causing the prediction of break-even period to be only 10 years, which is a very appealing and promising business proposition. Another unique thing about HTC is that it does not emit toxic waste to the environment, unlike landfill waste, and has a very low greenhouse gas emission, which makes it almost carbon neutral. Now, due to its high efficiency, broader use, as well as its high environmental impact and sustainability, hydrothermal carbonization comes as a feasible solution to solve the growing number of landfill waste in Indonesia.